Okay, welcome to Lecture Online, and let's talk about the apparent magnitude, or otherwise the apparent brightness of stars. The apparent magnitude is a way to determine or to be able to communicate how bright a star appears. When we go out at night looking at the stars, we'll see some very bright stars, some very dim stars. Some stars can barely be seen. Now, why is a star bright, or at least why does it appear bright, and why does it appear dim? Well, there can be two reasons why a star appears bright. First of all, it may be a very big star, shines very brightly, puts out a lot of light, and is therefore easily seen. It could also be because it may be a smaller star, but it's really close to us. And because it's so close to us, it appears bright, but it may actually be a very dim star. A star may be very dim simply because it's a very small star and very visible, or it's a very bright star, but really far away. So at this point, when we talk about apparent brightness or apparent magnitude, those are interchangeable, we think of it as how bright does it appear to us from where we are. It ignores the fact that it may be a big star or a small star, it may be far away, may be close by, that doesn't matter. Simply how bright does it appear from our location here on Earth. So when it appears to be like a really bright star, it may be because it's big, it may be because it's close, we don't care. It's simply an indication that it's a bright star. So what scale do we use in astronomy to indicate the brightness of a star? Well, we have what we call an apparent magnitude or an apparent brightness scale. And it's numerical in such a way that when the number is smaller, it indicates a brighter star, and when the number is bigger, it indicates a dimmer star. And yes, it can actually become a negative quantity. A -1 magnitude is brighter than a 0 or a 1 magnitude. To illustrate that, let's take a look here and say, let's assume we have three stars. Star A has an apparent magnitude, again, that's how it appears to us, of -1. Star B has an apparent magnitude of 4. Star C has an apparent magnitude of 9. Well, that means that star A is brighter than star B, and star B is brighter than star C. But the question is, how much brighter? How does that magnitude scale work? Well, to indicate how much brighter star A is compared to star B, the first thing we need to do is find the difference between the two magnitudes. So we can say that the difference between the magnitudes, and this triangle here means difference, it's a delta symbol, that is equal to the magnitude of A minus the magnitude of B, or maybe I should just write the magnitude of B minus the magnitude of A. So that's equal to -1. I'll take that back. That's equal to 4 minus a -1, which is equal to 5. So the difference in magnitudes here between star A and star B is 5 magnitudes. What we then do is we take that difference and we use it as exponent of the number 2.512 raised to that difference in magnitude factor. So in this case, between star A and star B, we take the number 2.512 and raise it to the 5th power. And when you use your calculator and do that, you get 100. That means star A is 100 times brighter than star B, or star B is 100 times dimmer than star A. In other words, you would need 100 stars like star B to give an equal amount of light as star A. And that's how we indicate the brightness or the magnitude of a star. We can do the same for star B and star C. Notice that the difference in the magnitudes here also is 5 magnitudes, which would indicate with the same formula that star B is 100 times as bright as star C, and therefore you would need 100 star Cs, or stars like star C, to have an equal amount of light output as one star B-type star. Now, how much brighter is star A compared to star C? Well, if star A is 100 times brighter than star B, and star B is 100 times brighter than star C, then star A is 100 times 100, or 10,000 times as bright as star C. We can use this equation right here. We can say 2.512 raised to, and notice the difference in magnitude between A and C is 10 magnitudes, so we can raise that to the 10th power. And if you use your calculator and you punch this out, you'll get 10,000 indeed, which indicates that star A is 10,000 times as bright as star C. And that's how we use magnitudes. Now, that still doesn't give us a feeling of how bright that really is. Well, the brightest star in the sky is Sirius, and Sirius has a magnitude of about -1.4. That's the brightest star in the sky. So if someone says, I'm looking at a star of brightness -1.4, you know they're looking at Sirius, and you know that they're looking at the brightest star out there. 6 is the dimmest stars that we can see with the naked eye. If you go out in a clear environment, in the desert, in the mountains where there's no street lights whatsoever, and you look into the dimmest stars possible, they have a magnitude of about +6. So the difference between +6 and -1.4 is about 7.4 magnitudes, and that is about, I would say, about 20 times 10,000, 200,000 times different. In other words, we have the ability with the naked eye to see a difference in magnitude of about, I'll take that back, about 2.5 to 2.57. It's more like 100,000 to 1. Sorry, I was off with that. So it's basically a difference of about 100,000 to 1. Sirius puts out as much light, at least it appears to us from our vantage point, not that it may actually do that, but from our vantage point, Sirius gives off as much light as 100,000 stars of magnitude 6. If you want to see stars that are dimmer than magnitude 6, you need to use binoculars or telescopes and so forth. For example, the planet, or it's no longer a planet, it's now the trans-Neptunian object, Pluto, has a magnitude of about +15. So Pluto is a very dim object. That's why it took so long for us to find it, because it's so tiny and so hard to see. You need a fairly large telescope, and among the myriad of stars out there, there's this tiny little dot that slowly moves across the star relative to the stars, and we finally found it that way in 1930. But again, you can imagine at +15, it's a fairly dim object, very difficult to see. So now you kind of have a feeling of the concept of a magnitude scale, a concept of what's visible and what's not visible to the naked eye, what the brightest object in the sky is as far as stars is concerned, and what the limit is of what we can see with the naked eye, and some very dim object like Pluto at +15. Well, Sirius is not actually the brightest object in the sky. We have some planets that are even brighter than that. Venus, for example, has a magnitude brightness of about -4.4, which makes it the brightest object in the sky besides the sun and the moon. The moon is at about -12 at full moon, and the sun is almost at a -27. Of course, the sun is by far the brightest object. So now we have a pretty good feel of the brightness of objects in the sky. The sun at -27, Sirius, the brightest star, at -1.4, and the dimmest object we can see at +6. And in the future videos, we'll get more of an exposure to all these various things. One thing I wanted to show you is maybe a scale, a table. So for example, if the difference in magnitude is 1, 2, 3, 4, 5, 10, 15, 20, what is the difference in apparent brightness as far as the absolute, or I shouldn't say absolute, but the comparison in how much light they put out? Well, at 5, we know that this is equal to 2.512 to the 5th power, which is equal to 100. At the magnitude difference of 10, that was 2.512 to the 10th power, which is equal to 10,000. At 15, this is equal to 2.512 to the 15th power, which is equal to 1 million. And 20, a difference in 20 magnitudes, is 2.512 to the 20th power, which is equal to 100 million. So if you have two objects in the sky, one that has a magnitude that is 20 greater than the other, for example, a plus 1 and a plus 21, that's a difference of 20, then one would be 100 million times as bright as the other, or the other would be 100 million times as dim as the other. Now, of course, 1, that would be equal to 2.512 to the 1st power, which is 2.512. And then if we want to get these other ones, that's 2.512 to the 2nd power, 2.512 to the 3rd power, and 2.512 to the 4th power. This is approximately equal to 6.5, this is approximately equal to 16, and this is approximately equal to 40. Those are not exact numbers, but close enough for our purpose. And so you can see that if you know the difference in magnitudes, you can then see how much brighter or dimmer one object is over the other. And that's why we use the magnitude scale, and in this case, the apparent magnitude scale, because there's another scale in astronomy where we use the absolute magnitude scale, how bright they actually are. But that's for a different video coming up.